VinFuture Prize, a new global science and technology prize for humanity from Vietnam. One VinFuture grand prize of $3 million. 3 additional special VinFuture prizes valued at $500,000 each. VinFuture Prize honors science and technology work that creates or has a high potential to create meaningful change in the everyday lives of millions of people. Join us to make a change for a better future.
Greetings everyone, and a heartfelt welcome to our esteemed colleagues tuning in from all over the world. On behalf of the VinFuture Foundation, I'm delighted to welcome you to the third InnovaTalk webinar of 2025. My name is Vizung, and it's my pleasure to be your moderator for today. Now, we turn our attention to one of humanity's oldest and most inspiring science, astronomy. This discipline has profoundly shaped our understanding of space, time, and matters, while also serve as a catalyst for groundbreaking technological advancements. In today's data-driven era, the emergence of AI has drastically transforming the field, equipping scientists with powerful tools to process and interpret vast cosmic data sets with remarkable speed and accuracy. And to delve into this exciting development, the VinFuture Foundation is collaborating with the International Astronomical Union to host the InnovaTalk webinar on astronomy, AI, and societal impact. Before we begin, we would like to express our sincere gratitude to the International Astronomical Union for partnering with us on this important InnovaTalk webinar. Their enduring dedications to the advancement of astronomical knowledge and fostering global collaborations make them an invaluable partner for today's discussions. Together, we aim to explore the exciting ways in which the fusion of AI and astronomy can propel scientific discovery forward and contribute to meaningful progress for communities worldwide. And now, it's our pleasure to introduce our chair for today's webinar, Dr. Vanessa McBride, the Science Director and Acting Head of the Center for Science Future at the International Science Council. Joining her on this esteemed panel, we have our distinguished speakers, Dr. Tomasz Kacprzak from the Swiss Data Science Center, Scherrer Institute. And we are also honored to welcome our special guest, Associate Professor Pham Ngoc Diep from the Center for Astrophysics and Science Explorations, National Space Center, Vietnam Academy of Science and Technology. And to begin today's sessions, we are delighted to invite Dr. Thái Hà Lê, Managing Director of the VinFuture Foundation, to have an opening remarks and share the visions that brought us together for today's webinar.
Thanks, B. Good day, everyone. On behalf of the VinFuture Foundation, I'm delighted to welcome you to the third InnovaTalk webinar of 2025 of VinFuture Foundation's titled Astronomy, AI, and Societal Impact. Whether you are joining us from an observatory, a lab, or just your favorite coffee shop with a strong Wi-Fi connections, we are pleased to have you here. Astronomy has always been a field that sparked the imaginations. After all, who among us hasn't looked at the star and asked what's out there, followed closely by, do I have enough data storage to analyze it? In today's world, those age-old questions meet the new age tools as artificial intelligence is helping scientists unravel the cosmos faster than ever, sometimes even before we finish our morning coffee. And we are honored to co-host today's discussion with the International Astronomical Union, IAU, an organization that has not only advanced astronomical knowledge for over a century, but also kindly remind us how small Earth is when they name the exoplanet. Our sincere thanks goes to Professor Willie Benz, the President of the IAU, for joining us today. And we're so excited to have an all-star panel. Our chair, Dr. Vanessa McBride, who brings both cosmic perspective and the earthly pragmatism in today's session. Our distinguished speaker, Dr. Tomasz Kacprzak, who works at the intersection of data science and the deep sky, and Associate Professor Pham Ngoc Diep, who is helping to shape Vietnam's future in astrophysics and the space exploration. At VinFuture, we believe science is not just about discovery, it's about impact. We support innovations that can improve the lives, especially in communities that often get left behind in global progress. And today's topic, blending the curiosity of astronomy with the power of AI, is a perfect example of that mission in actions. Thank you once again for joining us, and we hope today's webinar is insightful, inspiring, and perhaps just the right amount of starry-eyed. V, over to you.
Thank you, Dr. Thai-Ha for those insightful opening remarks. And now, we are honored to hear from Professor Willie Benz, the President of the International Astronomical Union, who will share insights into IAU's work and the importance of these discussions at the intersections of astronomy and AI.
Hello, everyone. I am Willie Benz. I am the President of the International Astronomical Union, the IAU. I am delighted to bring greetings from the Union to all participants in this first joint VinFuture Foundation and IAU webinar dedicated to artificial intelligence and astronomy. The International Astronomical Union is a worldwide union of professional astronomers. It was founded in 1919. Today, the IAU counts about 90 national members and over 12,000 individual members. The IAU mission is to promote and safeguard the science of astronomy in all its aspects, including research, communication, education, outreach, and development through international cooperation. Hence, the IAU is not just an organization that connects professional astronomers worldwide for science, research, and the development of technology and skills. It is also an organization that promotes the use of astronomy for the benefits of culture and society. This is precisely where the IAU mission meets that of the VinFuture Foundation. Using science and its associated technology, in our case, astronomy with all its suites of technological development, to make a difference in people's lives. Astronomy is a universally appealing subject that has inspired humanity for millennia. Curiosity about the cosmos has not only led to a better understanding of the universe, but also resulted in major technological developments that have benefited society. While astronomy is typically perceived as a science of discovery, its cultural importance, its place in popular imagination, and its multidisciplinary nature give it the potential to have a positive impact on society. Astronomers have been using machine learning and artificial intelligence for a number of years to help them analyze the vast amounts of data collected by their telescopes and instruments, or resulting from their numerical simulation, to identify galaxies, search for exoplanets, or discover new physical phenomena, for example. As well as making astronomy more efficient, it has allowed unprecedented amounts of data to be analyzed, revealing all sorts of treasures that would otherwise have remained hidden. Astronomers have helped develop the capability of AI to a level that is now transforming not only astronomy or data science in general, but also society itself. Once again, cutting-edge science is making its way into our everyday lives with all its benefits and risks. Finally, I would like to say how pleased the IAU is to be working with the VinFuture Foundation to organize this webinar on artificial intelligence and astronomy. I am sure that it will be an exciting event that will stimulate many thoughts. Thank you for your attention.
Professor Benz. After hearing from Dr. Thai-Ha and Professor Willie Benz, let's take a moment to watch a brief trailer exploring the key themes we'll be discussing today.
Astronomy, one of the oldest and most fundamental scientific disciplines, has yielded profound insights into the nature of space, time, and matter, while serving as a catalyst for significant technological innovations. In recent years, the rapid growth of data from ground and space-based observatories has established artificial intelligence as an indispensable tool in modern astronomy, enabling scientists to explore the universe with unprecedented efficiency and detail. Diving into the immense potential residing at the intersection of astronomy and AI, the VinFuture Foundation is collaborating with the International Astronomical Union to host the InnovaTalk webinar on astronomy, AI, and societal impact. The webinar is chaired by Dr. Vanessa McBride, the Science Director and Acting Head of the Center for Science Futures at International Science Council France. She holds various leadership roles across universities, research infrastructure, and science for development settings in an international arena. From the International Astronomical Union's Office for Astronomy for Development, she joined the ISC, where she bridged the gap between academic astronomy and the development communities. Joining her on the panel is the distinguished speaker, Dr. Tomasz Kacprzak, Senior Data Scientist at the Swiss Data Science Center at the Scherrer Institute. His focus is on interdisciplinary science in physics and artificial intelligence, in particular on applications of machine learning and high-performance computing to solve otherwise untraceable problems in physics and cosmology. Joining the discussion is a special guest from Vietnamese scientific community, Associate Professor Pham Ngoc Diep, astrophysicist. He serves as the director of the Center for Astrophysics and Science Exploration at the Vietnam National Space Center, part of the Vietnam Academy of Science and Technology. Since December 2019, he has held the positions of Associate Professor and Senior Researcher at VNSC. With the participation of esteemed experts, this InnovaTalk webinar will delve into the growing interdependence of astronomy and AI and examine their potential transformative impact on both scientific advancement and broader societal implications. Don't miss the opportunity to listen to key insights from our esteemed panelists on astronomy, AI, and societal impact.
Without further delay, let's welcome our esteemed chair for today's webinar, Dr. Vanessa McBride. Dr. McBride is the Science Director and the Acting Head of the Center for Science Future at the International Science Council. Throughout her career, Dr. McBride has held various leadership roles across university, research infrastructure, and science for development settings internationally. From the International Astronomical Union Office for Astronomy for Development, she joined the ISC when she bridged the gap between the academic astronomy and the development communities. Please join me in giving her a warm virtual welcome to the stage.
Thank you very much, V. So as an astronomer and a science director of the ISC, it's a real honor to be here today to chair this discussion. I'm grateful to the VinFuture Foundation for this opportunity to discuss three of my favorite topics in astronomy, artificial intelligence, and societal development. And all of these are linked in some way by the International Astronomical Union, and they offer some astronomy for development. I also want to say a thank you to the VinFuture Foundation for the work they do actually on behalf of scientists in promoting the value of these scientific breakthroughs through the VinFuture Prize. So today I just wanted to talk to you a bit about a context for AI and why the International Science Council is interested in the intersection of AI, science and societal development, and then talk a bit about how it's accelerating science, changing science itself, and then hand over to some of my esteemed experts on more of the topic expertise. I think we all know that artificial intelligence is everywhere. This is the kind of working definition that has been revised a few times. It's the definition used by the OECD, and that AI is a machine-based system that can infer from the input it receives how to generate some outputs. And for those of us who are a bit older, we may remember the first not so intelligent artificial intelligence, little Clippy, that was around as an assistant in the mid-90s. But we've come a long way since then, and we see the pervasiveness of artificial intelligence. We see it when we unlock our phones. We see it when we open streaming platforms in terms of the machine learning recommender algorithms. We see it applied on virtual shopping portals in terms of the pattern matching algorithms that it provides to help make our lives easier. And I think this ubiquitousness of artificial intelligence has been enabled in some sense by much cheaper data infrastructure and cheaper compute infrastructure. So bringing these two, the data and the compute together this way has really facilitated the kind of breakthroughs that we see now and we come to expect as normal in our everyday lives. But AI is also a priority on the multilateral agenda. We see that last year in September at the United Nations Summit of the Future, the Global Digital Compact, which was released as part of that huge international meeting, had an objective that specifically related to AI and socio-economic development, which was around enhancing international governance of artificial intelligence for the benefit of humanity. There have been a number of other draft resolutions. There's two with the words highlighted in the central panels there that also relate to artificial intelligence, its benefits for sustainable development and for capacity building. And a report at the end of last year from the UN AI initiative, which looked at governing AI for humanity. So really is everywhere that we look. But let me take a moment to tell you a bit about the International Science Council and why we're interested in this. So we're a non-government organization that works at the global level, and we catalyze and convene scientific expertise and advice on issues of major concern to science and society. We have quite a broad membership of science organizations. We have 45 international scientific unions and associations. One of those is the International Astronomical Union. And we also have about 140 national or regional organizations that might include academies and research council. And in Vietnam, our member is the Vietnam Union of Science and Technology Associations. We also have 14 affiliated bodies. These are either research programs, such as the World Climate Research Program, or observation systems around oceans or climate observing. So there are another 14 of those that, together with other organizations, the International Science Council co-sponsors. And a little bit about our strategic priorities. They can be encompassed roughly in these 5 boxes. We work to advocate for free and responsible and inclusive practice of science. We work around setting an international science agenda, but also allowing science to set the agenda where it's internationally important. We work to navigate evolution of science systems. And we work as well to create a platform so that science can be used to inform policy making at the multilateral level. And all of this sort of works through some kind of science diplomacy. And just taking a look at 3 of these, it's quite clear that artificial intelligence has a strong impact in at least 3 of them. And I think if we thought about it, we would see that it has impact across the board. We see it setting the international agenda. We've already seen that. We see it changing the way that we actually do science. And we see the ethics of it having some impact on how we practice science in a free, responsible, and inclusive way. So in terms of what we mean by artificial intelligence accelerating science, here are just two brief examples, one from physics and another from biological sciences. And we really see that the advent of these artificial intelligence algorithms has accelerated science. AlphaFold is a AI combined with a protein folding algorithm developed by Google in collaboration with scientists that accelerates the discovery of protein structures. And this can have huge potential impacts on socioeconomic development because it has potential for accelerating drug discovery. More on the fundamental science side, the picture on the right shows you a kind of an event in a particle accelerator. And here a bunch of these algorithms are used to look for anomalies in data. And these kinds of anomalies might help us to discover new physics outside of the models that we currently use to understand physics. And we'll have many more of these examples from our distinguished speakers. So this kind of shows how AI is accelerating science, but it also has the potential of changing really how we do science itself. Because the scientific process is a kind of a process where we come up with a hypothesis, we gather data to test that hypothesis, we might refine the hypothesis, and then we look for more data to substantiate or to refute that hypothesis. And often this process takes a while. We work through collaboration with other scientists, we work through the training of graduate students as part of this discovery process often. But we also see developments around AI, such as the Google Co-Scientist, which is beta at the moment, that offers the possibility of really accelerating and changing this process and potentially even replacing some of the key actors in this process by interaction with a principal investigator. Also in the academic community, we see how AI might help us to revise teaching and learning. So the proliferation of generative AI means that the way that we have graded written work before and tested the knowledge of students has to change. So we're really seeing these impacts across science. The ISC's work in this area up until now has been around a study that looks at preparing national research ecosystems for AI. This is a publication that came out earlier this year, and it presents 18 case studies from countries across the globe that looks at how they might be preparing their policy frameworks in terms of policy for science, their research infrastructure, and their capacity building efforts around using AI science. Also developed last year a short guide for policymakers, which is more general than AI, but does encompass AI, and it looks at evaluating these rapidly developing technologies. And the idea here is to form a bridge between the high-level principles and what you might actually want a policy to say. And so this is a very short document, which just mostly consists of a checklist of things to consider when you are thinking about developing policies around emerging technologies. So please do have a browse of some of these reports on our website, and we'd be very happy to hear from you. So the ISC depends very much on the expertise of its member organizations, such as the IAU, and their individual members to convene this kind of shared understanding of the issues that affect science across the disciplinary and geographical boundaries. So the kind of work that we put together in these reports really comes from the insights that we gather through individual members of our membership organization. And it's those kinds of inputs that can lead to the shared understanding that can provide the basis for the expert insights that we can provide to policymakers at the multilateral level. So I think with that, I'd like to take this opportunity to hand over to some of those experts for the rest of the session. I'd like to introduce our distinguished speaker, Dr. Tomasz Kacprzak, the Senior Data Scientist from the Swiss Data Science Center, to tell us a little bit more about AI and astronomy and its applications. Thank you.
Thank you very much for the introduction. I hope you can all see now my presentation. And let's get started. So first of all, it's a real pleasure to be giving this talk. I have been working on the intersection of AI and astrophysics for quite a while now. So I'm delighted to share some of my findings in this talk, as well as introduce more other projects that are delivered by my colleagues in the area of astronomy and in the area of climate science. Let's start with the connection between those two domains. The way I look at it is it's both astronomy and weather and climate sciences. We are looking at the sky. We are looking out, and in the case of climate and weather, we are just considering things that are happening very close to us, so our atmosphere. And in terms of astronomy, we're looking far away from us into galaxies, into our own galaxy, into the things that are between galaxies in the bigger groups. So in this talk, I will tell you quite a lot about astrophysics, specifically in the area of cosmology. The field of applications of AI in astronomy is vast, and I will introduce those on which I work the most closely, which is cosmology, and search for new physics and testing physical models on the cosmological scales. And then I will also talk about how that science that we do in astrophysics is connected to climate and weather, how these fields overlap and co-developed throughout the last decade in terms of AI. All right, let's get started. So these two spheres, one of them is looking at the sky very far away from us. So what we see is a lot of galaxies. If we look beyond our own Milky Way, we will see some areas in the sky where there's more galaxies, with, for example, these bright dots, and areas where there are fewer galaxies, so these blue areas. And not only galaxies exist in the sky in cosmological volumes. We also have sorry, just go back a little bit. We also have other corresponding fields. We can probe dark matter through the effect of gravitational lensing. We can probe galaxy shapes and see how galaxies evolve inside their environment. So there are multiple connected physical quantities that we can observe on the scales of the universe throughout its history. So this evolution in history is very slow, but nevertheless we can probe it by studying objects like galaxies that are very far away, give us information about the past. As well as galaxies that are very close, that give us information about recent universe history. And similarly for weather, we look at variable quantities, temperature, specific humidity, wind speed, they all close to us together, but they are very much connected in one physical system. So what we're dealing in scientifically is complex physics, complex evolving models. They are interacting of multiple physical fields across large areas, and they are both solved by very expensive numerical simulations, which are run on large supercomputers. And we have only limited data that can help us to pin down the right model and right parameters, which is very important for understanding, on one side, the physics of the universe, on the other side, our local weather and climate. So I'll talk about three strands. First, two of them will be in cosmology, and one of them will be in climate. First will be about how to extract information from our limited data. We have only one sky after all. This will be about testing physics such as gravity, dark matter, dark energy on cosmological scales, and how to improve these measurements using artificial intelligence. The second will be how to simulate the universe using artificial intelligence, how to make these expensive numerical simulations much faster and cheaper. And then finally, I'll move to practical applications and impact on the society in the form of climate, of accelerating and improving weather prediction. Through the interaction with dark energy. So it all comes together into a tug of war between the gravity, which wants to bring things together, move things closer, and dark energy, which is the cosmic acceleration effect, which wants to expand space in between objects. It's a very simple concept. It's quite complicated physics, but nevertheless, for the purpose of this seminar, this is what we need to understand. The earliest picture of a cosmic microwave background looks more or less like this. It's a very simple statistical object, which can be summarized using a very straightforward measurement of the temperature power spectrum of the cosmic microwave background. So we see a number of data points on this plot, and they contain all the information there is to know about the physics of the cosmic microwave background. Of course, there are caveats, there are other smaller effects that affect that, but in the big picture, this is our statistical object that we are dealing with, described by the series of these data points. However, since the Big Bang and the afterglow of the cosmic microwave background, the universe has been evolving and under laws of gravity and dark energy. And we are interested in studying the properties of gravity and dark energy and the evolution of these components in the universe. So what you see here is a numerical simulation of a large-scale matter distribution in the universe, which, as you can see, is collapsing the structures and making the universe more complicated, from relatively smooth, like we've seen already at the early universe, to very complicated network of filaments, voids, and halos. So we would like to extract the information from these fields to learn something about the universe, test the laws of gravity, find out whether Einstein was correct in a large-scale universe, as well in the local scales. And this is what we're going to look at is the shells coming from taking just a little slice around the spheres. And if we look at the universe that we think we live in today, this is a simulation again. It creates this type of patterns. On the other hand, if we increase the matter density, so we increase the effects of gravity, it would look more or less like this. And if we increase the dark energy, so we make the universe dominated by the expansion of space, we'll have a simulation that looks like this. So now, as you can see from these patterns, we can learn in which universe do we live in, with dominated by dark matter, dominated by dark energy, and exactly what are the proportions of these components. From our observations, we know that we are living already in the dark energy dominated universe, but we need more precise measurements of this type of parameters. So our dark matter density, for example, is one of these parameters. We need the measurements to basically pin down the laws of physics and understand the model in totality. And for example, if we look at this plot from a scientific paper recently published on these topics, we can see that a prediction from our cosmic microwave background, which is this red circle here, which is an extrapolation from our early universe model to today. And we can see the measure of from the type of data that I showed from the evolution of the universe in this other larger uncertainty contour. So these are all measurements. We show where our measurement points us to, and as you can see, they overlap. But what the game is about is making these measurements more precise, making these contours smaller, and knowing exactly what the values of these parameters are. And we find out whether there is consistency between various measurements, or if there is some discrepancies that may give us hints about the laws of physics that we don't know yet about. So we need to increase the precision of measurements to test the laws of physics as cosmological scales. This is also a picture of, if you were to look at the sky, how the dark matter maps would look like. That dark matter are created with techniques of gravitational lensing. This is beyond the talk, but this is a simulation. And there's a little moon here to guide the eye and understand the dimensions of this. So again, the regions where there is more light and the colors are lighter, that means that we would measure there more dark matter in these places. And in typical inference paradigm, we would predict some theory which would create these data points that you've seen, for example, for the case of cosmic microwave background. We would have some large-scale structure observations, so maps of dark matter that we can measure from our telescopes, and would compare using the statistics and make the measurements, as you can see here. But here's where the AI comes in. Instead of figuring out which statistics of the sky we need to look at, we can actually ask the neural network to create the best, most informative statistics. So to analyze the observations and tell us what are the measured values of parameters and their uncertainties. So here we replace the theory prediction from a very straightforward equation. I mean, it's a complicated equation, but nevertheless, it's something we can write on a piece of paper. It's a bit more complicated than that, but I think that's a fairly good description of it. Instead of doing that, we just run a lot of numerical simulations and let the machine compare the simulations to the observations and give us the measurement. And the machine is able to learn more information from these complicated patterns in the field. For example, here the dark matter measured dark matter field, because it can actually learn from very tiny features or things that we cannot really just comprehend very well as humans, and extract information from all these small things. And indeed, I was leading the team that did this measurements for the first time, introduced these measurements to the community. This is the first forecast that we have done, and we found that if we use machine learning, which is the blue contour of the convolutional neural network, we make the measurements on the same kind of apples to apple comparison with previous statistics that we have used. We gain a factor of 2 in measurement precision. So we go from the red uncertainties to the blue uncertainties. You can see the blue uncertainties are narrower, which means we increase the precision. If we wanted to increase the precision using conventional methods, we would need twice the amount of sky data to include in the measurement. So we'd have to run our telescope for twice as long. So this is quite remarkable. We are able to use AI and numerical simulations to improve our measurements by a factor of 2. And we don't need to observe as long, or equivalently, we get more information from the same data. And if we increase the resolution of our dark matter maps, we gain even more. So the AI is able to extract even more information from the small patterns. So we were before in this area. If we have high map resolution, we go to this difference. So higher is better. And we are going to outperform our traditional measurements by a factor of 4. So this is very important. We need to increase the resolution, and we need to make better simulations. So the first practical measurement that has been done like this was also led by my team at ETH Zurich and Swiss Data Science Center. We used a very simple neural network at the time, and we used the data from the kilodegree survey. And this is the first AI-based measurements of dark matter maps, which managed to shrink the contours from blue to red this time by a factor of 2. So you can see that the area inside the outer contours has shrunk massively. So this was the first measurement. It actually attracted some media attention. So we were advertised by, for example, MIT Technology Review. And from there, I'm currently working on projects inside a Dark Energy Survey, which is a large observational cosmological program, to perform such measurements. And we're going to have these measurements very soon. Hopefully, I can share it with you then as well. The state-of-the-art measurement of dark matter parameters, for example, dark matter density versus dark energy density, has been recently made by the Hyper Supreme Pham project. It is this very large, very precise camera mounted on the Subaru telescope, and a really state-of-the-art, very high-resolution images of the sky. This is how the survey looks like. This is an example of the image of the sky that was used. So the galaxy positions and shapes were analyzed to create these dark matter maps in these areas of the sky. And here you can see again a comparison between the measurement accuracy of deep learning, which is the artificial intelligence method, and the traditional method. And you can see that they managed to shrink the size of the contour, so increase the precision of the measurement by a factor of 2 or more, which is fantastic. Yes, and then this is the dark energy survey. We are performing measurement with various complementary fields of the same sky. So this is going to be first multimodal measurement, hopefully for cosmological. Very good. And then in the remaining of my talk, I will talk about accelerating numerical simulations with AI. So cosmological simulations play a crucial role, as you can already see from the topic before. They are providing an input to the simulation-based measurements with artificial intelligence. So if we want to have higher resolution maps that we can simulate to match the quality of the observations, we need a faster and more precise simulations of dark matter and other quantities. So you can see here is one of the state-of-the-art simulations from Flamingo Consortium, and it creates multimodal simulations, so simulating multiple fields. For example, on the large picture, we see the gas, and in the zoom in, we can see the dark matter density. So this is a really fascinating, very complicated simulation, and it takes really a lot of computational resources. There's also a lot of other fields, very complicated physics that are happening at the intersection of stars and large-scale scaffolding of dark matter. So, for example, here on the bottom, you can see gas temperature, and you can see some of these explosions of massive stars, so supernova explosions blowing out these gas out to the outskirts of these big structures and affecting the large-scale picture of the universe as well. So being from subgrid, very localized phenomenon, all the way to the large-scale phenomena through this type of effects. It's very hard to just simulate it, and especially if you want to use it in practical measurements, it's even harder. So that's where AI comes in as well. And here's an example of one of the first super resolution AI, which works on low resolution simulations and enhances its quality. So we only need to run low resolution simulations, for example, the ones on the left, and then the AI system will be able to generate a high resolution for us. So this is the true high resolution that the scientists have run. And this is the AI version of that. And the AI one only used the low resolution as an input. And of course, it was trained before. So as you can see, they are really very close to each other. This is just the start. These things will improve and already have improved massively since the first work on this. This is a recent example of multimodal simulation, where we have the full simulation and we have the AI surrogate of that. And I'll play the movie again. This not only creates the dark matter, but also other accompanying fields. So velocity, gas surface density, or H1 surface density is neutral hydrogen. So it can be used to combine measurements from various types of observations of the sky if we have that. And in the last part of the talk, I will tell you about how AI can accelerate and improve climate and weather predictions, and what are the connections with astronomy. So first of all, when we were working on our machine learning applications to measuring cosmological parameters from the large-scale dark matter maps, we created a deep learning tool that works on the STEER. At the time, it did not exist. It was 2018. We created one of the first methods that actually does that and was used in practice in the cosmology community. It's called DeepSphere. It's an open source project. So if you would like to use it, please just go to the GitHub and download it. And it was based on graphs. So we represented the sphere as a graph, and each pixel in the image of the sky was one point on the graph, and they were all connected together. This is also very useful because if we don't have observations on the entire sky, we can just use a part of the sky as a graph. And the graph architecture allows us to make all the operations needed to analyze this data with AI very fast. Then some of the weather scientists also picked up this code, and in 2020 wrote DeepSphere Weather, which was using our spherical graph representation of the sky and representing our atmosphere with these type of graphs using the same engine that we created, and was able to train on various fields of the weather simulation and weather observations. As you can see on the left, there was the actual data, and on the right, this is what the machine learning was predicting. So it's also very close. This is one of the first prototypes of such system. And since then, one of the first very, very successful models for weather, it was Google Mind's GraphCast, which was published in 2023, and also some earlier versions were available, where they also represent our atmosphere as a graph of nodes. There was some crossover between these projects, but overall, you can see that the weather community is using very similar technology. And so this was the first model that consistently outperformed the numerical simulated weather prediction. So it was data-driven, so it managed to encompass not only the numerical predictions, but also historical data. So it was this why it was becoming better than the numerical simulations. And they did not accumulate simulation errors. That was also very important. And when it comes to real-world impact, GraphCast is, for example, predicted very accurately the landfall of the Hurricane Lee in Nova Scotia 9 days in advance, which allowed people to adjust to this much easier, much earlier. So another advantage is that you can run it on your laptop. You don't need a large supercomputer to do this. Okay, and
just to notice, we're just wrapping up in the next minute or two.
Yes, that's perfect. Exactly. So the AI-based weather forecasting system was first deployed already in the European Center for Medium-Range Weather Forecasts. It was first one in production model and demonstrated 25% improvement in forecast accuracy over traditional method. It uses much less energy to produce this forecast with AI, and they're using advanced graph neural network transformers. This is the plot showing how it consistently beats predictions of the position of a tropical cyclone by roughly 50 kilometers compared to the traditional methods. And just to, in the last 30 seconds, a nice property of these systems, they're open source. So Aurora is a publicly available foundation model for Earth systems where you can download it and you can install it on your computer and you can start working with it. It's not only weather, but also a lot of other variables. And at the Swiss Data Science Center, we're also working on such applications. We have a partnership with Federal Office of Meteorology and Climatology in Switzerland and the Swiss Supercomputing Center. And there are these two projects, Speed to Zero and Deep Down. If you're interested, you can look at that. And we can improve. We are aiming to improve everything starting from nowcasting, so very short-term weather, to long-range forecasts. And this is just an example how AI can improve the resolution of our data of Switzerland. Thank you very much, and I will leave you with this final slide. Just to highlight, we have these massive astrophysical data sets, we can solve difficult problems in data science, which can then propagate into other aspects and other applications. And we can heavily leverage the open source culture and data sharing across different countries and across different disciplines and take advantage of this to accelerate the progress and lower the energy costs of all of these research and deployments. Thank you very much.
Okay, so let me just introduce our next speaker, fellow member of the IAU, Associate Professor Dr. Pham Ngoc Diep, who is the Director of the Center for Astrophysics and Space Science Exploration at the Vietnam National Space Center. Over to you, Dr. Diep.
First of all, I would like to sincerely thank the International Astronomical Union and the VinFuture Foundation for organizing this really interesting webinar and for giving me the opportunity to share our experience on astronomy in Vietnam and a little bit on the potential of AI for Vietnam. So first, let's address why astronomy. The most puzzling questions unanswered questions in astrophysics. To address this, it will advance the understanding of the universe and inspire the next generation. And we heard a lot of times from Dr. Thomas about dark matter and dark energy. Dark matter is an example of the unanswered stuff in the universe. This is a new type of matter which keep stars in galaxy moving like crazy, like our sun is moving about 220 kilometers per second about the galactic center. And we do need this new type matter to explain the observations as being shown in this simulations. A second example is dark energy. The thing that make our universe expanding, and actually we found that the universe is indeed accelerating, and the discovery of the accelerating expansion of the universe was given Nobel Prize in Physics in 2011 to these three scientists. So we have very little clue to explain the dark energy. And from the analysis of the relics of the universe, namely cosmic microwave background, we found that only 5% of the ordinary matter, the matter which we know about, and the rest is unknown. We don't know the nature of dark matter and dark energy, which occupies up to 95% of the universe. So we do not understand most of the stuff in our universe. As being emphasized elsewhere, astronomy is the oldest but also the most dynamic science. I show here several discoveries, important discoveries in the last decade, and I just want to highlight that from the first science images of the James Webb Space Telescope in 3 years ago, we were able to identify really massive and major galaxies with the age spreading from several hundred millions after Big Bang, million years after Big Bang, is a short time in comparison with the age of the universe. And this finding challenges the existing models of galaxy formation. So we see that important discoveries are being found continuously in astronomy. Another example to show the increasing influence of astrophysics in science is that the number of Nobel laureates in astrophysics in recent decades is increasing, and the increase of the members of the American Physics Society for a typical period is increasing the most. So regarding Vietnam, Vietnamese people were interested in astronomy since long, I guess like many, like other people all around the world. And so the feudalisms maintained the Royal Office of Astronomy, and the officers of this office were responsible for making calendars, keeping time, and predicting eclipses. Here I show one of the observatory in a province in the central Vietnam, before and after being restored. Concerning astrophysics research nowadays in Vietnam, it's essentially limited to a dozen of active astronomers all along Vietnam, and our small team, Department of Astrophysics, is the largest, and we work on different topics: stellar physics, high redshift galaxies, nuclear astrophysics, gravitational waves, and cosmology. And we can do frontier science thanks to a generous policy from the international collaborations, international communities, which release the collected data by most modern telescopes to the public. And another way to have data observing time is through collaborations. Here are examples of the large international installations that we use the data from. And here I show the number of IAU members from Vietnam and some other Southeast Asian countries for comparison. So you have the idea on our astrophysics community. A positive side is that we have many young people who are studying abroad or being trained abroad in astronomy, and this is a small survey which I did on the occasion of an article published in Nature Astronomy on astronomy in Vietnam. So this is an example of one of the telescope array which we use to collect the data. So I don't have much time, so I have to be quick. Yeah. Regarding outreach and education, there are many amateur astronomy clubs all along Vietnam, and there are planetariums and similar initiatives at various places, such as in Hanoi, Quy Nhơn, Nha Trang. And good introduction to astronomy and astrophysics is given to space science students at University of Science and Technology of Hanoi, and future high school teachers in universities of education in Ho Chi Minh City and Hanoi. And this is one of the beautiful picture taken by an amateur, and it was chosen as the image of the day from a very large international astro forum, Astrobin. And Vietnam take part in the International Olympiad on Astronomy and Astrophysics, and our student once got the absolute winner and many medals, gold, silver, and bronze medals. And there are two science exploration centers in Quy Nhơn and Hanoi for science education, and the one in Hanoi is to be completed by the end of this year. We have planetariums, optical telescopes for training. This is the 0.5 meter in diameter in Nha Trang Observatory, 0.6 meter in diameter in Quy Nhơn Observatory, and our college could take beautiful pictures of the sky. We always maintain international collaboration for our research and training. The collaboration with the East Asian Observatory is one example of that. And through the collaboration, our astronomers can use the facilities from EAO, and we maintain collaboration with many other organizations, such as the Paris Observatory, Bordeaux University, and Marseille University. And there are efforts to develop astronomy in Vietnam. SAGI is one of that, and the purpose of the project is to foster the collaboration between domestic and international researchers. And this effort is made by overseas Vietnamese. And we also collaborate between the astronomers inside Vietnam and outside Vietnam for research and training. And VANAT is another effort to do that. and also efforts, in particular by Professors Giang Chen Thanh Vân and Lê Kim Ngọc, to support the development of astronomy in Vietnam by organizing conferences, workshops, and schools. In terms of leading research team, at our department Astrophysics, we have been making a lot of effort to do research and training. I guess I don't have time to talk about our research. Some interesting one, like finding evidences for planets being formed in the earliest stages. Magnetic fields in the interstellar medium, or modeling to understand the multi-wavelengths data from observations. Yeah, this is the publications which we published during the past 5 years, and the training. So a little bit of comment on potential of AI for Vietnam. So you see that the roles of AI are emphasized in the talks of Doctors Vanessa and Tomasz. In particular, the role of AI in astronomy, and for Vietnam, there are some advantages to develop AI, and AI in Vietnam already being discussed a lot. Everyone is talking about AI nowadays. Like people are using chatbot, and people are being cheated by fake defects, and also there are people who lose jobs due to the development of technology and AI in particular. So recently, the government has focused on directing the implications of the national strategy on AI to 2030, and many domestic enterprises have been quickly grasped the trend and invested in AI. So in Vietnam, we have good natural science competencies, such as in STEM field and STEM education. And Vietnam also has IT, informatics, technology, human resources, and Vietnam has a young population who are very sensitive to technology. There's the presence of foreign tech giants in Vietnam, like Apple and NVIDIA and Intel. However, Vietnam faces several challenges because AI needs high quality human and financial resources. For example, we need computation power, and all around Vietnam, from survey, there are only 100 graphic processing units, and also to have high quality output for the solutions of specific problems for Vietnam. We need data from Vietnam, and data management and restriction is a problem which we need to address. And as being mentioned, we have the national strategy, but more concrete frameworks and laws to develop AI in Vietnam is still need to be completed. Vietnamese astronomy is on the development trajectory, and we are making a lot of efforts to develop astronomy in Vietnam. And this field fits very well our need, and we've been receiving a lot of support from international community, and we would like to have more of that, and also support from Vietnamese side. And AI may be the field for accelerating progress of astronomy in Vietnam. Okay, so Thank you.
So thank you very much for that. But and maybe we can dive straight in with the kind of building off that point that you've raised. I mean, it's fantastic to see the growth of astronomy in Vietnam. You've mentioned many of these kind of capacity building and community initiatives. I wonder if you can comment a little bit about the balance between funding applied sciences versus fundamental sciences in Vietnam first, and then we will look at that in a more global picture. So, Dr. Diep.
Actually, it's a difficult question, and in Vietnam and in other developing countries, I think applied science is given more priority. For example, if two projects are being sent to apply for funding, more priority will be given to the applied one. And I think this kind of event is also the opportunity for me to promote not only astronomy as a basic science, and I think that for Vietnam and many other developing countries, we need to develop applied science technology, and we still need to keep some room for developing fundamental science. And to directly answer the question, there is no black or white balance between fundamental science and applied science in Vietnam, but more priority is given to applied science, and people like me are trying to convince that we need room, we need support for fundamental science to develop in Vietnam.
Maybe I can also ask for your comment on this, Dr. Kacprzak, because I mean we can see some of the tools of applied science, being used in answering questions that relate to fundamental science.
Indeed, we have benefited tremendously from the development of artificial intelligence, both on the hardware side and on the software side or algorithmic side. A lot of that was driven by the commercially interested big companies, but a very healthy culture that exists in the machine learning community, even when it comes to the big technology companies, is that the open source and sharing is deeply ingrained in that community. So many of the big developments, some of the state-of-the-art, the most powerful, for example, neural network models, are being openly shared for people to download and adapt to another type of problems. Frameworks like PyTorch or TensorFlow that the students can just install and run on new problems are open source. This allows us to very quickly adapt to this new technological developments. So I've been very grateful for these companies who have put a lot of engineering effort into making these things work, for sharing that. It's absolutely fantastic.
Great.
I hope it stays like that.
We'll come back to that in a minute, actually, but I wanted to ask a bit about, the mechanism for the knowledge transfer. You spoke a bit about some of the techniques that are used in astronomy and that they've caught on as well in the climate modeling program. Where does that kind of happen? Because I often find, scientists are working in their silos, astronomers stick with astronomers, weather people stick with weather. Where do people find out about, a potentially transferable technology?
Should I go first?
Yeah.
Okay. Right. So in my experience, astronomy and applied domains experience a very beneficial relationship. Astronomy is like a frontier. We have very complex problems. We have very big data sets, we require a lot of computing power, and this is we have the inspirational value of getting people interested in solving these problems to answer some fundamental questions about the universe. So I've seen very often that problems were of various nature, large scale complexity, were first solved in astronomy, and then the students or the collaborators benefited from these new developments. The problem with astronomy is very special because we get data from the sky that's coming at us all at once. We cannot isolate and put a star in the lab and change something about it and perform a control experiment. No, we have a lot of data coming at us. We have to disentangle all of this. It's very complex, and I think that's also a feature of a natural world or human society. A lot of these processes are extremely complex, and that's why I think astronomers were also very good at going out into applied domains after doing some research at the PhD level or postdoc level. Going out to these applied domains and making a real impact. It's just a frame of mind, a way of thinking and applying, and kind of this big vision that was already ingrained from the beginning in astronomy, but that can be brought to the society.
Thank you. Dr. Diep, do you want to weigh in?
Yeah, it's a very good answer. So not much to add, but like many other fundamental science, astronomy, the discovery in astronomy can be, it can take a long time to be applied. Like in the case of the interferometer technique, which is applied in medicine, or even the GPS, if we don't correct for the general relativity effects, it will be wrong. So in general, it may take a long time for fundamental discoveries to be applied. But I think we all agree that discoveries, even the internet is coming from fundamental science, from CERN, if you remember. Astronomy, as Thomas said, it holds the most mysterious questions, and it's very attractive, and it is the excellent place for AI to be tested and to be developed with a vast amount of data. And from all this, we can teach our students both on fundamental knowledge and also technologies. And in astronomy, since the signals are very faint, right, we need to develop very modern instruments, telescopes. So it's also the way to advance technologies.
Yeah.
So that's
so for us as well. I think, coming from the International Science Council, we do put a lot of emphasis on actionable knowledge. Bridging this gap between creating the knowledge and then making sure that it's implemented in a way that benefits society. So I think what both of you have, illustrated today is that even for something like astronomy, a fairly fundamental science, asking questions about things that we're all interested in as human beings living on Earth. There is opportunity through our networks, through the tools and technologies that we use today to have a much broader impact. So thanks again to both of you. I'll now hand back to our MC for some questions from the floor.
A heartfelt thank you to all of our panelists for their invaluable contributions today. And now, before we move on to the highly anticipated Q&A sessions, we'd like to make an important announcement from our side. Submissions for the 2026 VinFuture Prize is now open for 1 grand prize and 3 special prize. We also take these opportunities to remind you of the VinFuture Nominator Recognition Programs, which honors those who help identifying groundbreaking scientific innovations with the potential to benefit humanity. And following that, we'd also like to highlight an initiative from our partner, the International Astronomical Union. Their Office for Astronomy for Development has launched a call for proposal inviting applications globally to explore how astronomy can contribute to sustainable development. Support is also available for those who need guidance with proposal writing, and the deadline to apply is May 31st. You can find more information on the IAU website regarding this initiative. And now, after hearing exciting opportunities from both the VinFuture Foundations and the International Astronomical Union, we'd like to transition to the highly anticipated Q&A sessions. We have already received a lot of fascinating questions from our audience, and we encourage you to continue to submitting them. Please feel free to actively participate by using the raise hand functions. And for people who prefer a more indirect approach, we encourage you to use the chat box. Simply type down your questions and we'll ensure that they reach the most relevant panelists within our time frame. And now, to start everything up, I would like to I have a question to our distinguished speakers, Dr. Tomasz Kacprzak. This is a very fascinating questions from our audience, and I would like to invite Jonathan Gallamay, a third-year physics student at Kansas State University, to directly talk to Dr. Kacprzak, please.
So my question is, it's about the DeepMind broadcast, and can this model be applied to predict the impacts of the Maiden-Julian oscillation, or MJO, on weather phenomenon like tropical cyclones, typhoons, and hurricanes? Additionally, can it be used for flood mapping and flood prediction in specific regions or parts of the country?
Sorry, the first part of your question was a little bit cut. Could you tell again which system do you have in mind?
It's the DeepMind GraphCast model.
Right.
As mentioned earlier.
Right. Great question. Indeed, so GraphCast has been recently superseded by another system called GenCast for generative. And also it's living in this family of foundation models. And I mentioned one of them is called Aurora, which is an open source model. So these foundations models, what they are building, it's what is called a generative AI for earth science, right? So it's a system that has the fundamentals to understand various phenomena, not only weather, not only climate, but also other earth system elements. So indeed, one can just take this model, and I think the providers of this model will keep improving it to include more and more components. One could take this model and adapt it to your specific problem. And some of the problems you mentioned are, yeah, extremely interesting, kind of mapping that you have in mind. I think that would be some type of task that this foundation model could be easily adapted to. Maybe not easily in terms of effort that needs to be put into it, but in principle, as a way of functioning, yes, that's exactly what this type of models are created for. So a very nice property of this is it's open source. It's something one can download and start working on and plug in your data into that model and do the modeling. It's like another very powerful tool in our toolbox.
Thank you, Dr. Kacprzak, and also Jonathan, for such an insightful discussions. And now, following this discussions, we would like to also invite one of our audience, Vindra Kanai from Trinidad and Tobago Astronomical Society, to unmute yourself and directly talk to our esteemed chair of today's webinar, Dr. McBride, please.
Hi, good day. Thank you very much for the very informative and insightful presentations. My question is regarding AI. What do you see as drawbacks to using AI in these areas, and how can these drawbacks be minimized or managed? I'd like to hear your input on this, please. Thank you.
So if I understand the question, it's some of the drawbacks of AI. I think there's quite a long list potentially. I think some of the things that we have to take care about with AI are to ensure that that we can reproduce, that they will only be as good as the training data that we give them. So we need to be aware of any limitations in some of the training data that these algorithms use to make their predictions. I think some of the other drawbacks potentially are that that many people are concerned about is the loss of creativity. So we see that from some of the creative industries and from science itself. They feel that some of the generative AI might take a fraction of, the creative industries. And I think that's something that we have to think about how to negotiate, whether it does do that or whether it's a stepping stone to something that's potentially more creative or accelerated. So those are two of the things that I think come up immediately, the ethical concerns and some loss of creativity.
Thank you very much.
Thank you, Dr. McBride, for one wonderful answer. And of course, our audience is also really eager to know more about the context in Vietnam right now. So for the next questions, I would like to invite Associate Professor Pham Ngoc Diep to answer this for me. So, Associate Professor Pham, how can international collaborations help Vietnam build capacity in both astronomy and also artificial intelligence?
As I mentioned regarding astronomy, you see that there is a very generous policy from the international community to release the qualitative data by the most modern telescopes. So in Vietnam, you see that the sky is not very nice. We cannot make observations from Vietnam, the high quality observations from Vietnam. So people like me who can do frontier research is thanks to the data collected by the international collaboration. And through the collaboration, we can also propose observing time to have the data which we are interested in. And through the collaboration, we have a framework to work with. We work on the most important problems in science thanks to the collaboration. From our team, we promoting the joint supervision framework, which is called Go-to-Tell. So it benefits not only the students but also our team in Vietnam. So many things from international collaboration, and nowadays with our international collaboration, I think we cannot do frontier science. And maybe I'm not an expert on AI, so regarding AI, Vanessa and Tomasz may have comments on the importance of international collaboration to develop AI in developing countries like Vietnam.
We have also received another question to Dr. Tomasz. Dr. Tomasz, can you please help me to answer this? What is the status on use of computer vision models in object detections and classifications in astronomy?
That's an excellent question. This is something I wish I had more time to cover in my talk. It's a vast subject, and in fact, one of the most impactful applications of machine learning are in the analysis of images taken by telescopes. Those are used in my research, but in a heavy post-process stage. So I use dark matter maps that were created using these images. But just to analyze the raw pixel images, machine learning methods have become indispensable already. So a prime example of it is a search for strong lenses Those are very rare objects where a galaxy, two galaxies are almost perfectly aligned along the line of sight, and the galaxy that is behind is distorted and strongly lensed. So it's a very powerful test of various astrophysical effects, including the nature of space-time through the measurements of the Hubble constant and properties of gravity and a lot of other things when can be discovered through these strongly lensed systems. So, but they are very rare. We have a lot of data to sift through, and just doing that using by looking at the images would be absolutely impossible. We have to spend very, very long time just looking at images. So machine learning is able to sift through millions of galaxy images or even billions of galaxy images very quickly, and can do it multiple times with various parameters and various configurations. And we can find these objects very fast and with a greater rate of false positives. So once we find this object, we would like to follow them up using spectroscopic or high-resolution telescope observations. And of course, we don't want to have false positives there because we would be just wasting our time on the telescope. So AI has been absolutely indispensable in this task. There are many more examples, but I think I'll leave it here.
Thank you, Dr. Kacprzak, and your wonderful answer have concluded our sessions of Q&A today. And now, as we have come to an end of the webinar, we'd like to extend our sincere gratitude to our esteemed panelists, Dr. Vanessa McBride, Dr. Tomasz Kacprzak, and Associate Professor Pham Ngoc Diep. Your expertise has illuminated the fascinating intersections of these fields and also their potential for a broader impact. We also wish to express our deep appreciations to the International Astronomical Union for the invaluable partnership in co-hosting this webinar. Their dedications to advancing astronomical knowledge and fostering global collaborations has been central to today's discussions. And of course, finally, we would like to thank our audience for your keen interest and engaging participations. We hope this webinar have sparked new perspective and encourage further explorations. Please stay tuned for future events from the VinFuture Foundations, and until then, best wishes to everyone.